Welcome back. In this lecture, you are going to learn about a new type of topology that is realized in twisted bilayer graphene. This is fragile topology, and it is not captured by the tenfold way classification of topological phases. We have learned previously that Dirac points in two-band Hamiltonians are protected simply by C2T symmetry, by this magnetic symmetry sigma xk. This guarantees that the Hamiltonian, the d vector of the Hamiltonian, allows for vortices to be stabilized. These vortices will always come in pairs of positive and right-handedness. And why is this? Because if we would start with a standalone Hamiltonian, with an atomic Hamiltonian, we would have to create these singularities of the wave functions from nowhere. This is the essence of a fermion doubling theorem introduced by Nielsen and Ninomiya in 1981. Dirac fermions in real symmetric Hamiltonians in two dimensions will always come in pairs when the total vorticity of the system is always going to vanish. So we can look at this by looking explicitly at the Dirac Hamiltonian around the Dirac points, where we have this form as we have seen before. Remember that we must make sure that we have a compatible basis at the k and the k prime values. We can change it to a real gauge by performing a unitary transformation to the Hamiltonian, which is written here in this form. And when we apply this unitary transformation, the C2T operator is actually going to be just complex conjugation, and the Hamiltonian will only have components in sigma x and in sigma z. That means that it's completely real. The sign here is going to determine what is the actual chirality of the Dirac point. In single layer graphene, we know that they will have opposite chiralities, but in twisted bilayer graphene will have the same chirality. So when we write the Hamiltonian in the real gauge, which we can write it, parameterize it by an angle that depends on momentum, we will have wave functions written in this form with a sign here in the first entry that tells you what is the winding or what is the chirality of the Dirac point. And we see that in order to have these states, we will have a region in between the Dirac points where we're necessarily going to have a jump in the sign of the first entry of the wave function. And this is a branch cut in the definition of the wave functions, which we'll call a Dirac string. The fact that we have a Dirac string here is that we can not really define smoothly the wave functions in momentum space. So now imagine that we are in twisted bilayer graphene where the two Dirac points of our system have the same chirality. Each of them will always also have a Dirac string coming out of them, but we have marked here in this string with a solid and a dashed stroke the actual winding of the Dirac point. That means what is the sign change in the sign change of the wave functions. And we can see that in order to connect these two Dirac points, we would require to twist this string. It's not really possible to connect it without twisting these two. So this is very similar to the topology of twisting of belts, and is in fact described by a topological invariant called the Euler class E2, which is defined when we have in two dimensions real symmetric Hamiltonians. So in particular, twisted bilayer graphene has such as twists, and it violates a doubling theorem because the vorticity of the entire system is not zero. But this is actually a very subtle type of topology that falls beyond what you have seen in the previous lectures, because this is really only defined for two bands alone. So unlike normal topology, which we cannot really trivialize it by adding some random trivial bands to the system, here we could remove these topologies just by considering an additional band. And an argument has been made by Unpark and Young, which I'm going to schematize here. So imagine that we do have two Dirac points of the same chirality, and we will just close the gap between these two bands with a third band that is where we're going to create, out of coupling with this additional band, two Dirac points of opposite chirality. They're connected by a Dirac string, which can seamlessly connect the two. Now we are going to move these Dirac points across one of the original Dirac points, and such that the Dirac string is starting to encircle the Dirac point. This Dirac string, what it indicates is the fact that there's a change in the sign on the first entry of the wave functions. And this means that when I annihilate them together, it will change the sign of the first entry in all of this enclosed region. It is exactly the same as a Dirac point of an opposite chirality. So when we do this transformation, now there's no problem whatsoever of closing the Dirac string between the two Dirac points and annihilate them. This means that just by coupling with a third band, with a trivial third band, we were able to completely trivialize the set of two bands that hosted the two Dirac points that we were interested in. So the trivialization is possible, and it's possible with by changing the number of bands and by coupling with trivial bands. This means that it does not respect the stable equivalence of topological phases that we've learned in the tenfold way classification, and it falls beyond this paradigm. So let us just show you a simple four-band model that has as the field bands two fragile bands with two Dirac points of the same chirality. Here is the model. It basically is nothing but two Chern bands coupled to each other. They have opposite Chern number, and they are coupled in a way that still preserves C2T symmetry. And here is the operator in the C2T operator in the four-band space, that is as the sigma space but also a tau space, and we just include coupling terms that still commute with this operator. So we can see that these Dirac points have the same chirality. We can bring the upper bands, the unfilled bands, which in this model are also fragile, so they are not trivial. And we can couple the unfilled with the filled bands, so we can remove the fragile topology by tuning the mass term in the Hamiltonian and tune it into a trivial phase. And this will be done in an extended phase transition where the filled bands are going to be coupled with the empty bands, and first they will join in a quadratic band touching, which will separate into two Dirac points that surround the original Dirac point of the filled bands, and you will see by that process it did not remove the Dirac point, but it changed its chirality. So now we have Dirac points of opposite chirality, which is compatible with an atomic band, with a trivial band. Although we looked at a specific example, the concept of fragile topology is broad, and it's applied to any topology that depends on the number of bands, and it can be trivialized by adding trivial bands. Surprisingly, this type of topology is often appearing in topological materials and topological matter. So this further widens the landscape of topological phenomena in quantum matter.